Yeah, so I think we're going okay. Guys, let's go ahead and get started. Thank you for being here in Zoom with me today. I appreciate it. Um, if you have any trouble hearing me or seeing anything behind me here, please do let me know. You can use your microphone if you would like to get my attention. You can also type into the chat. I am kind of watching my chat box a little bit. So if you can't use a microphone and you want to say something to get my attention, just go ahead and type a message into the chat. That would be fine. I've logged myself onto both my laptop and my phone. So I'm hoping that you guys can hear me okay. I'm hoping you can see the board behind me. This is where I'm going to be writing for the next, I guess, almost 2 hours. If you're having any trouble with the technical stuff, let me know. I'll do the best I can. The main thing is I'm hoping the internet will hold up on my end, especially for these next 2 hours. But anyway, yeah, you might have even seen a past video of mine that was recorded here. I'm at my summer home in Colorado visiting with my family this week since we had Tuesday off. I hope you guys had a nice holiday on Tuesday. I hope that this week is going a little bit easier for you in that sense. But I will be back next week in Fullerton. I'm going to be driving back over the weekend. So you can expect a normal week next week back in our usual classroom and everything else. This is just kind of a one-time thing for this one class only to talk here in Zoom. Also, I should mention that there is a homework assignment due tomorrow night. I should have time to answer some questions about it during our class today. If you want to, you can do that. It's a pretty fast assignment. The one that you're doing for tomorrow night, I don't think should keep anybody up very late. It's pretty straightforward. It's just plug and chug. Mostly of the stuff that was in the videos that you guys watched, that you turned in just last night. But it's pretty basic stuff, actually. So I'm hoping that the homework for tomorrow night won't be too bad. I am going to hang around in my office after class today. And then also tonight, like I usually do in the evening, I'm going to have my evening office hours. So if you do want to ask me more questions about anything, you'll have a chance to do that later today as well. Okay. Any questions so far? Are you guys all hearing me okay out there? Getting the message through? Okay, good. I'm seeing some thumbs up all over the place. That's great to hear. Okay, so I think I've set the stage for everything now. Again, thank you all for watching the video about sort of the homogeneous nth order constant coefficient differential equations. We're going to be reviewing that a little bit today. I also talked about this idea of a Wronskian matrix, and I want to just come back to that. And I'm going to use group work number 12 to do it. So this is in Canvas. You can open up the group work if you want to. Or I've written this question on the board, and you can just read it off of here as well. But this might actually work as a nice warm-up for what we're going to do today. So I thought I would just start with this, if that's okay. So this is the first problem off of group work number 12. So notice that it talks right away about this auxiliary equation. So remember that when you turn all of the d's into r's using the trial solution of e to the rx, you get this so-called auxiliary equation. This is the equation that involves r. I'm just reviewing from the video, right? This is the equation involving r whose roots you need to find, right? And I talked in the video about repeated roots or complex roots or what have you, right? But using those roots, we can write down the solution to our nth order homogeneous differential equation. So let's just suppose here, guys, let's suppose that there are 3 distinct roots, no repeats, right? No repeats here. So in that case, let's call the roots A, B, and C. And as you remember, when you find these roots, A, B, and C, you then have to build solutions to your differential equation. and they would be of the form e to the ax, e to the bx, and e to the cx. This is a basically a third order differential equation that we would be looking at here. I've got these three distinct roots that gives me these three solutions. And I just want to verify, guys, that these solutions are actually linearly independent. Remember that if I have more than two vectors, and in this case I have three, but at any time I have more than two vectors, I cannot just say, oh, they're not scalar multiples of each other, right? The scalar multiples reasoning is great when I have two vectors, but when I have three or more vectors, I've got to do something else. And at least in the context of differential equations, we can use this Wronskian to do it. So let's try and do it, guys. I'm going to go ahead and start doing a solution here for us. Let me remind you, this Wronskian, I write it as W, and you just plug in your functions here. So e to the ax, e to the bx, and e to the cx, right? Those are the inputs into my Wronskian. And this was, as I talked about in my video, this is just going to be a determinant. It's going to be a determinant. And let me remind you how you lay out this matrix, right? What you're going to do is put each of your functions into the first row of your matrix. So e to the ax, e to the bx, e to the cx goes right across that first row. Yeah? And then as I go down the columns, I have to take derivatives, right? Remember that? So I'm going to take the derivative of each of these. So the derivative of e to the ax is a times e to the ax. And the derivative of e to the bx is b times e to the bx. And the derivative of e to the cx is c times e to the cx. And we're going to keep taking derivatives down this matrix until it becomes a square matrix. So right now it's not yet a square matrix. I need to take one more derivative in order to make it a square matrix. And if I take another derivative of a e to the ax, I'll end up with a squared e to the ax, and then b squared e to the bx, and then c squared e to the cx, just like that, just like that. So this is my 3x3 matrix now, and I have to take the determinant of it, okay? So far, so good? Hopefully, just gonna see, I do see some good faces out there, that's awesome, that's very helpful. Okay, now to do this determinant, we can just use the arrow method. If you remember, the arrow method just involves recopying the first two columns of this same matrix again. So I'm just going to make two columns of what was the original matrix here. And then I'm going to do my little arrow method on it. Now, when I do this arrow method, guys, I'm going to go down these diagonals. But here's what I want you to notice, guys, about all 6 of these diagonals. All 6 of them are going to have an e to the ax, e to the bx, e to the cx on them, right? They're all going to have that. You can see on this first diagonal, there's an e to the ax, e to the bx, e to the cx. Well, you're going to get that on all 6 of these diagonals. So I am going to factor out the e to the ax, e to the bx, e to the cx. All right? And if you look at what's left, like what are the coefficients that are not part of those exponentials? On this first diagonal, I have bc squared, right? And then the next diagonal over, I have what? ca squared. And then on the next diagonal over from that, I have, I don't know if I'm drawing my lines very well, I think it's ab squared. And then we have to do the diagonals the opposite way. So I go this way and I subtract a squared b. And then my next diagonal, I subtract b squared c. And then on my next diagonal, I subtract ac squared. So there's 6 diagonals, right? The first 3 get added, the last 3 get subtracted, and I have factored out all of the exponentials because all 6 diagonals will have that exponential on it. So we can just factor it out. Right. Now, I have to tell you, the first time I ever looked at this problem, I tried and tried and tried to factor this part in the brackets over here. And I really found it difficult to do that because there were like 3 different letters. The A, the B, and the C are all kind of mixed together here. So eventually what I realized is that this is a lot better if I just figure out in advance how to factor this thing that's in the brackets. So I'm going to show you how to do it without really spending a lot of time explaining it. So we have e to the ax, e to the bx, e to the cx. It turns out that this part in brackets is actually b minus a times c minus a times c minus b. So I'm just going to ask you to trust me that if you were to multiply out the b minus a, c minus a, and c minus b, you would get these 6 terms that I've put in the brackets over here on the right. It's just algebra. And that's why I'm not really dwelling on this. It is just algebra. That's all it is. But as long as you're willing to trust me on that, we are now going to be in a great position to actually think about the value of this Wronskian. Guys, remember what it says in the original question. A, B, and C are distinct roots. If they are distinct roots, guys, that means that they are not 0. Not 0, not 0. None of those are 0. And these exponentials are also never 0, right? You probably remember this from calculus. The function e to the whatever, x, is never going to cross the x-axis. It's not 0. So nothing here is ever 0. The upshot of it, guys, is that this whole thing is not 0. Haha, right? Well, remember, do you remember the W test from my video? Actually, we're going to write down the W test in just a minute because it's the second problem on this group work. But the W test actually tells us that as long as the Wronskian of your functions is not 0, then your functions are Li. Your functions are linearly independent. So I'm just going to add that here, guys, right on the bottom of my board by the W test. And again, it's in your notes that you took on that last video, but I'll remind you what the W test is in just a minute. But because of the W test, right, the functions, the set e to the ax, e to the bx, e to the cx is Li. So that confirms it. That confirms it, at least for a case where we have 3 distinct roots. We can be pretty comfortable that the functions e to the ax, e to the bx, and e to the cx are Li. Everybody okay with that? Any questions? I'm keeping my eyes on the chat. So if you can't use a microphone and you want to get my attention, just throw any questions you might have in the chat. I'll be glad to help out. Okay, now for the challenging part of this. I don't have a very big board. You guys all know that I write pretty big and I spread myself out. So I don't have that luxury today. So I'm going to have to erase a little bit. I'm going to erase this question up here at the top. And erasing is a bit of an adventure because it's only about 50 degrees in this room that I'm in right now. And I do have a heater on, but it's a little tough to erase the board because it's cold. I didn't realize this until COVID, that a whiteboard does not erase very well if it's cold. So I'm having some challenges with it, as you can see. But I'm getting there. Okay. The second problem on that group work, I want to do number 2 as well. The second problem on this group work is actually to try to justify the W test. So I'm going to write this down. What was the W test? Let's just review it here quickly. It's what I just used a moment ago, but it says that if y1, y2, and ... up to yn are functions. So y1, y2, and y3, if these are all functions such that the Wronskian of those functions, so y1 up through yn, if the Wronskian of those functions is not 0 for some value, I called it x naught in the way I stated this test before, then my set y1, y2, and ... up to yn is Li. This is the Wronskian test, the W test, as I like to call it. Okay, let me get this back in front of me here. Hopefully everything readable so far. Okay, really appreciate those thumbs up, by the way. Thank you for doing that. It helps me just confirm that everybody's still hearing me out there and you can still see everything okay. This is the W test. We just used it on that last problem. We just used it. We took the Wronskian of e to the ax, e to the bx, e to the cx, and we showed that it was not 0, which meant that the functions were Li. What I would like to do on this problem is actually prove the W test. I would like to prove it now, show you the math behind it. Okay, so let's prove the W test. In the group work, if you do look at group work number 12, which is where this is coming from, if you take the time to look at that, what you're going to find is that I actually broke it down into like 6 parts. So I'm not going to lay it out into the 6 parts right now as we talk it through in class today. But if you do go back and review the group work, you'll see that I kind of break it down step by step. Let's remember how to prove. So here's my set of vectors, right, guys? I just underlined in blue what I'm trying to show right now. And this problem is a nice chance to remember what linear independence means. Right? Like, what is the definition? If you'll remember, to show that a set of vectors is Li, what we are going to do is we are going to assume that those vectors cancel out in a linear combination. So I'm going to write it this way, guys. C1 times Y1 plus C2 times Y2 and ... up to Cn times Yn is equal to 0. Okay? That's how I always start these sort of conceptual proofs about linear independence. If I'm really doing a computational problem, I would put a matrix down right now and I would do some EROs, that sort of thing. But in this case, that's not what I need to do. I just need to do it very sort of abstractly here. Does anybody remember what it is that I would like to show at this point about those constants, C1, C2, and so on? Can somebody help me with that, either in the chat or with your microphone? What do I need to show here?
I believe you need to show that each constant equals to 0.
Yakov, yes, that's exactly right. We have to show that these constants are all 0. So let's see if we can do that. Let's see if we can do that. So we're going to just keep that in mind, right? So maybe I'll even write that down. We will show that C1 equals C2 equals dot, 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 all the way over to Cn, that those are all equal to 0. That's what I would like to show. But I'm starting with this equation right here at the top. Now, here's the trick. And again, in the group work, this is actually sort of spelled out for you as to what to do. But what we're going to do, guys, is we're going to take this first equation that we wrote down, and we're just going to take the derivative of it all the way across every term on both sides. So if I just take this first equation and I take the derivative of it, what I'll end up with is C1 y1 prime plus C2 y2 prime and dot, 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 all the way across Cn yn prime still equals to 0. And then I'm going to take that equation and take another derivative of that. So C1 y1 double prime plus C2 y2 double prime all the way over to Cn yn double prime. And we just go dot, dot, dot all the way down, and we do this as many times as we want. I think we're actually going to end up doing it all the way until we have taken n-1 derivatives. So we go all the way across. The last one that we're doing here, guys, we're taking n-1 derivatives. Okay, so I'm going to go ahead and erase this one little line in the middle for a moment. I basically have this whole big collection of equations now. I have all of these equations that are all true, starting from my assumption. Now, if you're with me so far, is everybody with me so far, by the way? We all good? You know, this thing is just, thank you guys for the thumbs up, really appreciate it. This thing is just begging for us to put it into a matrix. It looks like we could put this into a matrix, couldn't we? Let me try and do it over here, just because this is where I have a little bit more space. I'm going to make a matrix out of this. And in the first row of the matrix, I'm going to put y1, y2, and dot, dot, dot up to yn. All right, and then in the second row of the matrix, I'm going to put y1 prime, y2 prime, up to yn prime. And I'm just going to kind of go dot, dot, dot down below that. I realize there's a kind of a glare on my board right here. That's just from one of the lights I'm using. So I won't fill in the whole matrix. But if we now multiply that by this column of the C1, C2, and so on up to Cn, then that is going to be equal on the other side of the equation to 0. Are you guys all able to see that okay? So this is on the right-hand side, it's just a bunch of zeros. On the left-hand side, I have my constants. And then the matrix on the far left is just the unknown functions, and then their derivatives, and then their second derivatives, and so on and so on. With me? This matrix over here, I realize I didn't really fill it all the way in, but can you see what it is? This matrix where you take the functions on the first row, and then you take their derivatives on the second row, and then their second derivatives on the third row. Guys, that is the matrix whose determinant is the Wronskian. This matrix right here, let me go ahead and give myself a little bit of room to add here. This matrix, right? This matrix has a non-zero determinant, right? This matrix has a determinant that is not 0, right? Because it's just the W matrix. It's the Wronskian matrix, actually. And we are assuming that those functions have a non-zero Wronskian. Great. So this matrix is going to have a non-zero determinant. What does that tell you about the matrix, by the way? If the determinant is not 0, what do you know about this matrix? Throw it in the chat if you're not sure. I'm sorry, If you can't use your microphone, you can write it in the chat. Yolanda and Jose have already sort of stolen my thunder, right? This matrix is invertible. It is invertible because the determinant is not zero. That's one of the big things we've known for quite a while now. So that's good news. This is an invertible matrix here. This is invertible. Guys, if the matrix is invertible, guess what? You can basically cancel it. You can multiply, you have an inverse for this matrix. You can cancel this matrix. You can cancel it by using the inverse of the matrix. I won't write all of that down. I'll just say cancel by using inverse. You can cancel this by using the inverse. That's it. And if you've canceled it, guys, then what are you left with here? If you've canceled it, then you're just left with C1, C2, and so on up to Cn equals 0, 0, 0, 0, 0, 0, 0. Right? That's what you're left with. You've canceled the matrix, so all you have is this column of constants equal to this column of zeros. That just means that all of those constants, they all are 0. And that's what we wanted to show. So thus the step y1, y2, and dot, 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 up to yn is Li. That's right. These vectors, these functions are Li. Are we good with this? This is the whole thing. Questions out there, anybody? Everybody good so far? Great. Well, that's group work number 12. So we're done with that. I just thought that was a nice warm-up because it reviewed the Wronskian for us a little bit. Let me go ahead and erase here if I can. I think it's warming up in here a little bit, so that's helping. I'm going to erase this entire thing. And we're going to take a fresh start on a new section right now. We're going to cover one section today. That's all we're going to do. And I don't think this will be too bad. So this is called 8.3 in our book. And this is going to be something that I'm going to call the annihilator method. The annihilator method for solving nth order linear differential equations. And of course, we've written that down in our nice brief notation several times previously, just L of y equals F. Okay. So I'm going to teach you guys how to solve L of y equals F today. That's what we're going to learn. And to do this, I need to explain a 3-step process. It's going to involve 3 steps here. And you're going to need to follow these 3 steps to solve L of y equals. By the way, guys, this is a big deal. I'm teaching you actually how to solve an nth order differential equation. It's not even homogeneous anymore. There could be some f of x on the right-hand side. Who knows? So the first step is actually going to be to solve the corresponding homogeneous differential equation. So step 1 is going to be to solve L of y equals 0 for basically the solution here. There's a name for this, guys, that I would like us to know. It is called the complementary function. And it's denoted y sub c of x. Y sub c of x. Now, just to be clear, this first step, you guys already know how to do it. This is the thing I explained in the second video that you guys watched for extra credit over the weekend or over the holiday. This This is done by just writing down the auxiliary equation, finding the roots of that auxiliary equation, keeping track of repeats and complex roots if you have them, and then spelling out the whole solution. We did several examples of that in the video that you just watched, and we're going to do several more today because we're going to be practicing this three-step process. So this is actually goes back to section 8.2. We've already learned how to do this one, and we're just going to be reviewing it today. Okay, so that's the first step. Now the second step is actually where we do something new. We are going to find just one, we're going to find one particular solution. And I'm going to write this as y sub p of x to the actual non-homogeneous differential equation that we have, right? So we're going to find one particular solution. I'm going to denote it as y sub p of x. And for this, I'm just going to say see below. So in a minute, we'll have some notes on this, and I'll explain how we actually do step 2. Because this is really the meat of this section, is how do we find one particular solution? Does everybody see the difference between steps 1 and 2? Step 1, I have a 0 on the right-hand side of my differential equation here. In step 2, I'm putting an F back in here. So that's the difference. This is homogeneous in step 1, and in step 2, what we have is not homogeneous. Okay, and then, excuse me, step 3 is where we just write down the final answer. Step 3 is just the general solution. And the general solution is yx equals y sub c of x plus y sub p of x. Right, so the third step is actually also kind of just a no-brainer. All you're doing in step 3 is adding together the complementary function and the particular solution from the first 2 steps. So step 3 is kind of a nothing. Do you guys remember the examples I did in my video that were like 9th and 10th order differential equations? They were the examples at the very end of that video. Those involved writing 9 or 10 terms down. So in step 1, your complementary function would have had 9 or 10 terms. It could be worse than that. I think last semester on my exam, I gave a 14th order differential equation, and there were 14 terms. Yeah, so why am I bringing this up right now? Well, what I'm going to tell you guys is that when you're doing problems on my homework or on my exams, and you get to step 3, technically, you have to write down those 9 or 10 or 14 terms again, because that's part of the general solution. Well, that's a lot of writing. So I'm actually going to give you guys a break here. And I'm just going to tell you that when you get to step 3, you can just write this down. If you don't want to recopy all of the complementary function and all of the particular solution, which might take half a page to write all of that down again, you can just write this down, and that will remind me that you know what the third step of the process is. So we'll be good on that. You don't have to I'm just trying to save you a little bit of writing. For step 3, you can just write this down if you don't want to write it all out again, and just save yourself some time. Okay, so this is the outline of the 3 steps. I'm going to erase it now, though, and focus on step 2. Step 2 is the new material for today. It's the annihilator method that I'm about to explain, okay? Let's do it. So I'm going to go ahead. We'll be using this 3-step process on all of the examples in just a little bit. So let's talk about step 2. So let's do step 2 here, because this is the main thing that we need to learn today. And I'm going to give you the strategy here first for how to do step 2. So I'd like to give you the strategy for step 2. And the strategy is the following. We are going to try to find an annihilator for the big F. Okay? Actually, sorry, I want to write that slightly differently. We want to find an annihilator, and there's a notation for the annihilator that you're going to be seeing me use today. A of D for the big F. And what I mean by that, put a little colon here so I can write this down on the next line. What I mean by an annihilator of a function, it's just some annihilator that when you apply it to F, it turns it into 0. Okay? By the way, when I say A of D here, this is just the notation, right? The D that you see here, guys, is actually referring to that same D that I was using previously. It refers to the derivative operator. So what I'm saying here, guys, is that I would like to use derivatives to annihilate F. F is going to be given to me in the original differential equation, right? I don't know what F is yet, but it's going to be given to me, and I'm going to have to kind of live with it. Why do I want to annihilate the capital F? Well, I'll show you. I'll show you why that's going to be, and then we'll talk about how to do it, how to find this annihilator. But the reason for it is that if you have L of y equals F, and you then annihilate both sides, so if you apply this A of D on both sides, so you just start with L of y equals F, which was our original problem. You hit it with A of D on both sides, but the A of D annihilates capital F and turns it into 0. What is so awesome about doing that? Well, now your differential equation is homogeneous again. And we already know how to solve homogeneous differential equations, right? If there's a 0 on the right-hand side, we're back in section 8.2. We find the auxiliary equation, we figure out what the roots are, we spell out the terms of the general solution, lickety-split, right? Really easy. So this is the idea. We would like to annihilate capital F so that it becomes 0, and in doing that, we will turn our differential equation back into a homogeneous one. Oh, I just wish I could jump through the screen to talk to you guys. I get pretty excited, but it's a little hard here in this cold garage. I'm trying. Anyway, so let's just practice, before we actually solve any differential equations, I just want to practice figuring out what this annihilator idea is. Let's just do a couple of examples here to kind of get the idea of it. So let's start real easy. Let's start with something really easy. Let's suppose that my function f of x is x squared. And what I would like to ask you guys is, can you think of any way to annihilate x squared by using derivatives? If I take one derivative of x squared, I would get 2x, right? What would happen if I then take another derivative? So the second derivative of x squared would then be 2, right? So you'd have 2x, then you'd have 2. What would be the third derivative of x squared? 0. Yeah, it would be 0. In other words, it would be annihilated, right? It would be annihilated. If I do 3 derivatives of x squared, I will get 0. So an annihilator for x squared would be 0. Absolutely true. And in fact, let's just kind of build off of that a little bit, guys. I'll do a second example. Suppose that f of x is just any power, let's say x to the k, but I want to make sure that k is a positive integer here. So k is like 0, 1, 2, or 3 or whatever. So if I had just a power of x, just some power of x, can somebody tell me, what do you think the annihilator of x to the k would be in general? How many derivatives do you think I would need to take to annihilate x to the k? Throw it in the chat, guys. If you don't want to use your microphone, that's okay, but throw it in the chat for me. I see one person has put it in the chat. Anybody else agree with that? K plus 1 derivatives. Yeah, thank you guys for those thumbs up. I really appreciate it. The A of D is going to be D to the K plus 1 power. That's absolutely right. That's absolutely right. Okay, so those are the annihilators of those powers of x. Let's try something a little harder. What if my f of x was e to the ax for a second? What if that was my function, f of x? Now, the reason I say that this one is a little bit harder is that if you just take derivatives of e to the ax, you could do that forever, and you're never going to get 0. Right? The derivative of e to the ax is a e to the ax, and then the second derivative would have been a squared e to the ax. We actually did those derivatives earlier on the group work. There is no power of d that is going to make this f of x turn into 0. We have to get a little bit more clever here. And here's the way we can do it, though. If we take just one derivative of e to the ax, one derivative of it, we will get a e to the ax. And if I want to cancel that out to 0, I can subtract a from it. This is the answer. This is the answer. And just to check it, I'm just going to check it right here, just in case anybody's doubting this. What happens if I take d minus a and I apply it to e to the ax? Let's just check it. Well, I'm going to take the derivative of e to the ax, which is a e to the ax, and then I'm going to go minus a e to the ax, and sure enough, that does equal 0. That does end up being 0. So the annihilator of e to the ax is d minus a. And this little blue writing at the bottom of my board is just checking that. It verifies that I really do have the correct annihilator there. Okay. Hopefully that makes some sense. Let's try another one. I'm going to erase the blue writing though, guys, if that's okay. Is everybody keeping up all right? Yeah? Okay, good. I am recording this session, so don't worry. It's not like you could never find this again. But let's try one more. Let's try f of x equals, actually, I'm going to do cosine of bx and also sine of bx at the same time. It turns out they both have the same annihilator, so I'm just going to do them both at the same time. Let's see if we can figure out what the annihilator of sines and cosines would be. By the way, guys, the more annihilators we can figure out right now, then the more differential equations we'll be able to use this strategy on. So we want to figure out these annihilators so that we can use these strategies that I'm gonna be practicing with you in the second half of our class today. So the point here is, I'd love to find as many annihilators as possible. Let's try to do it for sines and cosines. Now we had an example involving sines and cosines, I think in class last week, where we took two derivatives of either the sine or the cosine. It doesn't actually matter. If you take two derivatives of sine or cosine, do you agree that you will get back to sine or cosine again, but with a sign change? Right? There's a minus that comes into that. The other thing that's going to happen though, guys, when you take derivatives of cosine of bx or sine of bx, you're going to be pulling b's down, right? The little chain rule for derivatives. When you use this chain rule of differentiation, the b's are going to come out in front. So I actually claim that what you need to use here, let's make sure we get it written down, d squared plus b squared. I claim that that is the right formula. Let me see if I can just verify that up here for you. Let's just check this one as well. So let's just check this. If I do d squared plus b squared and I apply that, let's just check it for the sine of bx. We'll just do the sine case. Let's see if we get 0, right? So what is this? This is equal to two derivatives of sine of bx. Sorry. It's going to be two derivatives of sine of bx plus b squared sine of bx. That's actually what the calculation would be. But guys, if you take two derivatives of sine of bx, you're going to get negative b squared of sine of bx. Yeah? And now, if you look at the two terms, they absolutely cancel out to 0. And it's just equal to 0 again. So my annihilator for sine of bx or cosine of bx is going to be d squared plus b squared. Okay? Does that make some sense? So guys, so far I've explained how to annihilate powers of x, exponential functions, and sines and cosines. Now, obviously that's not everything. That's not every function you could ever see, but it's a pretty good start. And actually, we can do even better than this. And I wanted to pull up for you. I'm going to actually share my screen for a second with you guys to show you that there is an entire table of these annihilators. So let me just try to see if I can not mess this up too badly. I hope that you guys can see what I've tried to share on my screen for a minute. This is a handout that I'm going to be giving you on our next exam and also on the final. You will have this handout for the rest of the semester. And take a look at the first 9. The bottom half of this page is just a table of integrals. But the top half, as you can see on the top half, I basically have spelled out what these annihilators are. And I've just explained like a few of the ones at the beginning of the list. But look, for example, if I wanted to annihilate like powers of x together with exponentials, together with sines and cosines, we can actually do that. Now, it gets messy. You can see that there's a little a and a little b that floats around in these formulas a little bit. So it does get a little bit messy, but the good news is you don't have to memorize any of this. I'm going to give you this table. You can use this table. You should use this table as much as you need to, okay? So I just wanted you to know that this table is in Canvas. It's in the special handouts folder, right? So if you need to look that up, you can find it there. But I just wanted you to know that we don't need to memorize all of these annihilators. And I'm not expecting anybody to do that. I will give you the annihilators. Okay, I'm going to make a couple of quick remarks, guys, and then we're going to take a 10-minute break, okay? But a couple of quick remarks, and then we still have to see how this strategy helps us solve differential equations. It's great to calculate annihilators of functions, but we have to see what's the purpose of it. How does it help us? So I've got to get into that. That's going to be after we take a short break. But I want to make a couple of remarks first. And maybe to even do one example. So let me just erase all of these preliminary examples. And I'm going to make a couple of remarks and then do one example, and then we'll take a 10-minute break. Okay? So here is, I'll just call this remark. And there's going to be two of them. I'll call them A and B. So the first remark is that putting a constant, just I'll call it C, putting a constant as a scalar of any f of x does not change the annihilator, the A of D. It doesn't change the annihilator. So for example, guys, if my f of x was, 8x squared, then the annihilator has no effect from that 8. It is still just e cubed. The 8 does not do anything to this annihilator. You're still going to take 3 derivatives of 8x squared and get 0, right? So constants don't really affect the annihilators. That's kind of the point I'm making here. Constants don't have any effect. And that's true for any f of x. It doesn't, not just for x squared. That would work for any f of x whatsoever. Okay. The second remark is that if your f of x is a combination of several terms, so maybe I'll write them as f1 of x plus or minus f2 of x plus or minus f3 of x and so on. If you had a f of x that had several terms added or subtracted together, then the annihilator of such a function. Now, this is one that people sometimes get wrong, so let's be careful here. To do the annihilator of a bunch of terms like this, you have to do the individual annihilators and multiply them. So A1 of D times A2 of D times A3 of D. If those are the individual annihilators for the individual f of x's, you then have to multiply those annihilators together. That's the point. That's the point. Okay, so let me just give you one example here, and then we'll take a short break. So for example, is everybody with me, by the way? All right, I see a couple of thumbs up out there. I love it. I love it. I love it. Thank you guys so much. Glad this is making sense, I hope. So let's take this example. Suppose that f of x is equal to 8x to the 5th minus 3e to the 2x cosine of 5x, and then plus 2x e to the 3x sine of x, and then minus 4x squared e to the 7x. Let's take that f of x and let's find the annihilator of it. Okay, so this is going to be a big one. So this will be a nice example to kind of wrap up the first half of our class with. Let's say that was the f of x on the right-hand side of my differential equation. And now what I want to do is figure out how to use derivatives to annihilate it. The trick is going to be to figure out the annihilator. I'll start my solution here. To figure out the annihilator of all 4 terms. I actually have to just look at them individually and find the annihilators of all four terms here. So could you guys all grab your chat boxes for me? And could you type into your chat box what the annihilator of 8x to the 5th would be? Just type it into the chat. I want to see lots of responses here. Not just one or two. Let's get everybody typing it in. Just want to make sure you guys are with me today. What is the annihilator of 8x to the 5th? Just that first part. Okay, now I'm starting to get my chat boxes going crazy. Yes, it looks like we have 100% agreement. Everybody is writing down d to the 6th, and that is awesome. D to the 6th is correct. The 8 does not matter, and if I want to annihilate 5 powers of x, I have to take 6 derivatives. Okay, let's go on to the second term. The 3 that is in front of the second term does not matter. Remember, we just made the remark that constants don't really matter. But we have to figure out how to annihilate e to the 2x times the cosine of 5x. To do that, guys, we really need our table. We need that table, e to the 2x. Maybe I can try to reshare this one time real quick. E to the 2x times the cosine of 5x. If you're able to see my shared screen here, you can look down on that table. I think it's item number 6. I think it's number 6. E to the 2x times the cosine of 5x. Let's try and write down this annihilator. It looks like it's going to be d squared minus 2ad. In this case, a is 2, so that would be 4d. And then plus a squared plus b squared, which is actually 29. So 2 squared plus 5 squared is 29. So that's item number 6 in the table. Again, you're not memorizing this table. You're just looking at the table and plugging in the a and the b to write that down. Okay? The next term is actually kind of similar to that. The 2 does not matter in front. But then where I have this x here, this x is actually going to have a little bit of an effect on this annihilator. So we have e to the 3x sine of x. Let's go back one more time. I'll share this one more time here. If I have an x times e to the 3x times the sine of bx, I think that's actually number 9 in the table. So we used number 6 for this term. And now on number 9, we have d squared minus 6d, and then plus a squared plus b squared would be 10, I think. But there's also a k value. Do you see that x to the k in front of number 9? So I'm using number 9 right here. The x is raised to the power of 1 right now in my function. So k is equal to 1, and I see an exponent of k plus 1. So I actually have to square what I have there. So d squared minus 6d plus 10 gets squared in that term. Okay. And now here is where, I'll stop sharing again for a second. Here is where we get into trouble with me not having a very big board to write on. I have very little space to put this last term. The 4 here doesn't matter. And I have an e to the 7x. Normally, so let me just see if I can squeeze it here. Normally for e to the 7x, I would use d minus 7. But because there's an x squared in front of it, if you look back at the table again, and I believe, I won't pull up the table for everybody again right now, but I believe it's item number 3 in the table. You have to cube that d minus 7 because of the x squared that's in front there. Okay? And so those are your 4 individual annihilators. And according to this remark B down here, according to the remark down here, if I figure out the individual annihilators, then my final answer for the annihilator of everything is to multiply those annihilators together. So I'm gonna write that down here, guys, and then let you take a look at it. This should be the final answer. Can you believe that? If I want to figure out how to annihilate something as messy as the capital F that I started with, I have to create this very complicated derivative operator, right? That serves as an annihilator, but we can trust, assuming that my table is correct, we can trust that this will annihilate capital F of X and turn it into 0. Yeah. Does that make sense? Everybody following this okay? Questions here? Okay, great. I see a few thumbs up out there. I hope the rest of you are not thumbs down. Hopefully it's all making some sense. Well, I tell you what, I would like to take a 10-minute break like we usually do. So if you want to step away from your screen for a few minutes, at about 12 minutes after 11, I'm going to come back and explain how we use these annihilators to actually solve differential equations. So that's actually the real punchline of the whole thing. So come back in 10 minutes and I'll explain that for you. I'll see you guys shortly. Guys, if you're out there within the sound of my voice, in about 1 minute, I am gonna start back up again, so. This would be a good time to make your way back over towards wherever you're watching this from. And again, if you do have a camera that you can turn on, it's always nice to see faces out there. So. Also, by the way, guys, if you've started the homework for tomorrow night, and if you have any questions on it, maybe just jot them into the chat. 8.2 is the homework that's due tomorrow night. And I may have some time at the end of class today to take up 1 or 2 of those homework problems, if there are any. If not, no worries. Like I said, it's not that bad of an assignment. I don't think there's any true false read. I can't remember for sure, but I don't recall that there are any. I don't have the assignment in front of me, actually. Sorry. Okay, well, guys, I am going to trust and hope that you are all still out there and still hearing me and seeing my board okay. We're making it through this okay. Just this one Zoom class. Hopefully it's not going too badly for you. But we have not gotten to the punchline yet, right? This whole thing was supposed to be, how do we solve a differential equation using this annihilator method? I would like to spend sort of the rest of the time that we have learning how to do that. So we're going to use the annihilator stuff that we just learned to do some examples. The best way to explain the annihilator method to you guys really is true, is just to show you some examples. So I've got the first one on my board here, and we're going to work through this one together. I'm going to go through the first one pretty slowly. Step by step, but we're going to see that there's some shortcuts with this that will actually make this go pretty smoothly on some of the later examples. So here we go, guys. By the way, is everybody able to hear me and see me okay out there still? I see a couple people's faces, but I would love to get some feedback from more of you. Okay, good. I see lots of thumbs up. Awesome. So you guys made it back. Sweet. So let's try this one right here. Let's try to solve y double prime minus 16y equals 3 to the 3x. Now, do you remember the 3-step process? That whole business about annihilators is really for step 2. So let's start with step 1. Let's start with step 1. Step one is where we solve the associated homogeneous differential equation. I'm going to write it using the D notation here, guys. So on the left side, I have d squared minus 16 of y. And because I'm on step 1, I'm going to ignore the capital F and just use 0 for the time being. Now, one of the things that you learned in the videos that you just watched over the weekend is that we can write down the auxiliary equation for this differential equation by just changing the d's to r's. So it's just as simple as writing down r squared minus 16 equals 0. Okay, and if we do that, oh, you know what? Oh no. I'm so upset with myself. Guys, I have miscopied this question. I am going to fix this. This 16 was not supposed to be there. It was supposed to be on the other side of the equation. Oh no. So I'm sorry, we're going to make a slight little edit here. At least I figured it out fairly quickly. The 16 should have been on the right side of the equal sign. I'm so sorry. So my derivative operator is actually d squared minus 1, not d squared minus 16. Can everybody get that fixed for me? It's not a big deal, but I just want to make sure we're all on the right page. Okay, so d squared minus 1 is what the operator should have been. I just changed the d's to r's right here. And r squared minus 1 equals 0. I think everybody can solve that for r. We get plus or minus 1. Plus or minus 1. Notice that there's no repeat roots and there's no imaginary roots. These are two distinct real roots, and so I can right away put down the complementary function. It would just be C1 times e to the x plus C2 times e to the negative x. And let's put a box around that so that we can refer back to it later. So it's always a good idea to box these complementary functions and particular solutions. So this is what we would have, right? So remember, guys, the solutions that you're looking for, they always have the form e to the rx, as long as the roots are real and as long as there's no repeats. That's the whole thing we have to do. And I have two values of r here, which are 1 and -1. So I get two solutions, which are e to the x and e to the negative x, and I build them out into sort of a linear combination. So far, so good? I'm looking for some feedback out there. Okay, I see so quite a few thumbs up. Is anybody wanting to ask me a question about this? This is just step 1. And it's really based on the previous section, right? This is the stuff that you watched the videos on before. So far, I'm not even talking about annihilators or any of that yet. Okay, let's go to step 2. Step 2.
Sorry, I had a quick question.
Oh, yes, please, Yasmin, go ahead.
So I know that for all the problems you write down, d squared and just writing it like that, but if we were
Yes.
to write it on an exam or like on a homework assignment, go straight to the auxiliary equation, solve for the homogeneous or the complementary, would that be counted as wrong?
No, I would probably accept that. So like in this case, if you just looked at this left-hand side and you just wrote down r squared minus 1 equals 0, I'd be okay with that.
Okay.
I do think it's good not to skip too many steps. You know, the thing is when you show your work, then you know that I can give you partial credit for anything. Even if you make a mistake, I can still give you some credit. If you just jump right to, like some of you might have been able to just write this down immediately from the original problem. But if you were to make a mistake, and if you didn't show any work, then I have a hard time like figuring out how to justify partial credit. So that's why I would recommend trying to show some of these steps. It doesn't take very long. Does that make sense?
Yes, thank you.
You're welcome. Anybody else have a question so far? Okay, let's press on. I'm going to go to step 2. And the first thing I want to do, guys, is I want to write down the annihilator of the right-hand side. This is the capital F right here, yeah? This is capital F, 16e to the 3x. Can somebody tell me what will be the annihilator of 16e to the 3x? Can you either tell me with your microphone or put it into the chat? What is the annihilator of 16e to the 3x? This goes back to what we were talking about before the break. The 16 doesn't matter, right? It's just a constant, so we can just kind of ignore that. What is the annihilator of e to the 3x, guys? I think there's a lag on my internet or something. Here comes some answers into the chat finally. Okay, yes, Quentin, Nathan, Yolanda, thank you so much. D minus 3, right? If you forget that, just use the table of annihilators, right? We showed that earlier today. So this is just D minus 3. Okay, now here's what we're going to do. We are going to apply that annihilator on both sides of our differential equation. So I'm going to apply this annihilator. So I'm going to have D minus 3 of d squared minus 1 of y equals D minus 3 of 16e to the 3x. But we already know that D minus 3 is going to annihilate the 16e to the 3x and turn it into 0. So what you have here, guys, is actually a new differential equation that is now homogeneous. This one is homogeneous because there's a 0 on the right-hand side. We can write down the auxiliary equation now, right? Here's my auxiliary equation for this problem, for this step 2 that we're doing. Just change all of the D's into R's. That's what we learned how to do in the previous section. And if we look at these roots, we have 3 and we have plus or minus 1. Now I have a little observation for you here, guys. These roots plus and minus 1, do you realize that those are actually the roots that we had already found in the first step? Those are what I actually like to call, let's come back up here. I like to call those the old roots. They are the roots that were there from the very beginning. And of course, they're still here now because after all, the r squared minus 1 is still showing up as a part of my auxiliary equation. So this is the old roots, whereas the 3 is my new root. This is a new root here. I don't know if you can read that very well. It just says new root. So we have a new root here. And if we were going to now write down the solution to this problem, what would we be writing down? We would be writing down y of x equals c1 e to the x plus c2 e to the negative x plus c3 e to the 3x. And it looks very similar to the complementary function. And in fact, so this first part is actually the same as the complementary function, and it's only the new root that has created another term here. And guess what, guys? This term here, it becomes your particular solution. This is the y sub p of x part. Remember, there's a complementary function in step 1. There's a particular solution in step 2. And then ultimately, we're going to get to step 3 where we just add them all together. Now, there is one big, does everybody have their eraser handy? There is one big thing I'm going to change. And that is that although C1 and C2 are just constants that we will leave as arbitrary constants, this particular solution is supposed to be very specific. It is supposed to have a specific value. There should not be a C3 in our particular solution. I am going to change it. I'm going to use my eraser. I am going to change it to a different letter altogether, and I like to use capital A, capital B, capital C, something like that. I'm going to change it to an A, and by doing that, I'm going to remind myself that A actually has a value. It has a specific value. Let's see if we can figure out what it is. So what I'm saying, guys, is that the form of the y sub p of x is a e to the 3x. But this is where a is to be determined. Okay, so the form of the particular solution is something like that. Remember, the complementary function is the first 2 terms, and then the last term is going to be the particular solution. But we can actually solve for A. Guys, let's take this particular solution and plug it back into the original differential equation. Let's take 2 derivatives of it. Let's just do that. What is the first derivative of a e to the 3x? Well, that's just 3a e to the 3x. And then let's take the second derivative. Well, that's just 9a e to the 3x. So I just take those derivatives of this particular solution. And now I can plug into the differential equation. Let's try it. Let's plug the second derivative, that was 9a e to the 3x, minus y itself, which was a e to the 3x. And we're setting that equal to 16 e to the 3x. Is everybody with me on that? That's y double prime. So this one is y double prime minus y on the left side. But what am I taking the derivative of? It's the form of the particular solution. Now you can probably look at that. You can cancel the e to the 3x's from everywhere. And when you do that, I'll put it over here on the side. 9a minus a is actually 8a equal to 16. So actually, this is what I was talking about, guys. We can get a specific number for a. It's just equal to 2. That's why I don't want to call it C3. If I write C3, then I'm thinking, oh, it's just any random number. It's a constant. But we can actually solve for it. And so we found out that it's equal to 2. And so now the particular solution is actually 2 e to the 3x. Does that make sense? So we solve for the actual constant here by plugging the form of the particular solution back into the differential equation. So guys, let's go to step 3. Step 3 is where you just write down the final answer. I'm going to actually write it all the way out. C1 e to the x plus C2 e to the negative x plus 2 e to the 3x. That's the whole thing. Remember, this is the complementary function added to the particular solution. That's really what you have there. All right. Any questions on that? Everybody okay? You might wonder, is there ever a scenario where you would solve for C1 and C2? That would only happen if you had initial values provided to you. So if somebody told you what y of 0 is, or what y prime of 0 is, then you could solve for C1 and C2 for that initial value problem. But unless you have initial values, your final answer will have C1 and C2 in them. Okay, let's try another example. Let's practice a little bit more on this. I've got 2 more examples, I think, that we can hopefully get through today, just to make sure everybody is good with this method. Each example that I'm doing is going to try to show you something new. So don't just assume that you only need to see one example of this. It does depend a lot on the problem. Let's try another example. Let's try to solve y double prime minus y prime minus 2y equals 10 times the sine of x. Excuse me. Okay. So I'm going to go slightly faster through this first part of this. I'm going to do step 1. Step 1 is where we write down the auxiliary equation. I'm going to do what Yasmin suggested, and I'm just going to go straight to the auxiliary equation. Change these derivatives into r's. So r squared minus r minus 2. And remember that in step 1, we ignore the right-hand side. We don't even think about what it is. So I'm just focusing on the left side here. This thing factors really nicely. R minus 2 times r plus 1. And so I get my roots, which are 2 and negative 1. And these are what I'm going to call the old roots. These are the roots that are kind of the old roots. And so I can write down my complementary function immediately, C1 e to the 2x plus C2 e to the negative x. And so there you have it. That's the first step. Okay, again, all of that comes from the section 8.2. That's the older material. Now let's go to step 2. And I need some help with what is the annihilator of the sine of x. The 10 does not matter, but could you guys use your chat box for me again? And could you type in what is the annihilator of sine of x? Remember, it's on the table if you need to look at the table. But this one you might already know. The annihilator of the sine of x. Let's see. Anybody got it? Somebody besides Yolanda. Anybody else want to confirm? Throw it in there. Yeah, Ryan, Joel, thank you guys so much. D squared plus 1. Yeah? It's just right out of the table. If you take two derivatives of sine of x and then add sine of x to that, you'll get 0. Absolutely. So the annihilator here is d squared plus 1. Now, I'm going to go a little shorter than I did on the first example. I'm going to streamline the process, and I am going to immediately get the new roots from this part of the operator. So the d squared plus 1 is going to give me, r squared plus 1 equals 0. What are the roots of that? Well, I already put them down. Plus and minus I, right? Plus and minus I. Those are the roots corresponding to this annihilator. And if you remember, guys, when we get, I'll just steal a little corner up here. If we get sort of a pair of complex conjugate roots, this is what was in the video that you watched. We can build two solutions out of that. One of them is e to the ax cosine of bx, and the second solution was e to the ax sine of bx. So we can make these two solutions whenever we have imaginary roots, like we do right now. Now, in this case, the a part is actually 0. Right? So in this case, a is 0, and the b part is just 1 in my pair of complex roots here. So if I plug in 0 for a and 1 for b, I'm going to get solutions that are cosine and sine of x. So what is my form of my particular solution? The particular solution is going to coincide with these roots only, the new roots. Everybody with me on this? The old roots are aligned with the complementary function. The new roots are aligned with this particular solution. So the way it's going to look, guys, is something like this. Capital A times the cosine of x plus capital B times the sine of x. That is the form of the particular solution. Again, I don't want to call these constants C3 and C4 because that will cause me to mingle them up with the C1 and the C2. These two constants actually have specific values. So just like in the example we did a few minutes ago, I would like to solve for A and B. Now, in order to do that, I'm going to plug this particular solution into my original problem at the very beginning. To do that, I need to take a couple of derivatives here. So I like to take my derivatives first. So the first derivative here of this particular solution would be negative a sine of x plus b cosine of x. And then if I take a second derivative, that would be negative a cosine of x and then minus b sine of x. So we just get the first couple of derivatives here in order to plug in on the left side. And now I'm gonna actually do the plugging in. I hope I have enough room here. Let's see if I can squeeze this in. On the left side, I have y double prime, so that would be negative a cosine of x minus b sine of x. And then minus the first derivative, which is negative a sine of x plus b cosine of x. Okay, be sure to use parentheses here, guys. Make sure we don't have any algebra mistakes. So this is y double prime minus y prime. And then I have to go minus 2 times the original y sub p, which is a cosine of x plus b sine of x. And this is where I need a little bit more room. I'm going to squeeze an equal sign over here, guys. 10 sine of x. Sorry, that got a little bit tight, but hopefully you can read that okay. All right, so I'm erasing the complementary function, guys, but we are going to need it again. We are going to need to write that down again in step 3. So now, oh boy, I would like to solve for a and b. And this thing at the bottom of my board is kind of messy, but the way to do this is to group together all of the cosine terms on the left side. So let's do a little algebra here. And on the left side, I'm going to try to kind of group the cosines and the sines together. The right-hand side should be the sine of x. So I'm going to kind of try and organize the terms into this kind of a layout. I want to lay it out like this. The right-hand side is 10 times the sine of x. That was given in the problem. And on the left side, I just want to kind of gather up. I have to look at what I have down here at the bottom of the board, and I have to gather up all of the cosine terms. Right here, I see a negative a of cosine, and then this is sine, this is sine. Here's a cosine with a b in front of it, right? There's a b there, but don't forget there's a negative. It's negative of b, so I'm going to subtract b. And then let's keep reading. As I go over to the far right, I have minus 2a times cosine of x as well. All right? So those are the cosine terms. This one, and this one, and this one. Now the other terms are all having to do with sine of x, and we should gather those up as well. I have a negative b, and then, oh, you know what? Yeah, negative b, and then this is actually plus a. It's a double negative, so it's plus a, and then minus 2b. Okay? Am I going too fast? Guys, following how I'm getting all this stuff? I'm just grouping together. There's a bunch of terms here on the left side. I'm just grouping all of the cosines together, and then I'm grouping all of the sines together. Now, this thing here, by the way, how many cosines do I have on the right-hand side of the equal sign? How many cosines do I see over here? None. None. So the cosine part on the left had better be 0. Because they have to balance, right? The equation has to balance. So however many cosines are on the right side has to match how many cosines you have on the left side. And the same thing with the sine, I have to balance that as well. And I have 10 sines on the right side, so I would have to have 10 sines on the left side to balance that. And what you get here, guys, is just a couple of easy equations. You just get a couple of easy equations. So the first one here, negative 3a minus b equals 0. And then the second one is a minus 3b is equal to 10. That's it. And of course, from here, you could just put these two equations into a matrix and solve it like we've learned how to do earlier in the semester. I'm gonna make your life easy and just tell you what the values are. This is pretty easy to solve. Turns out that A is equal to 1 and B is equal to -3. So you can check me on that, but I'm pretty sure that those are the correct values for A and B. And so my particular solution, I'm gonna go ahead and put it over here. My particular solution, so here was the form. This one was the form right here. And now I know what A is and I know what B is, so I'm gonna substitute them in. A is 1 and B is -3. So here you go. This is your particular solution. We should put that into a box so that we don't lose track of it. That's gonna be an important part of our final answer. Everybody okay here? All of this was step 2. Coming up with the particular solution. Questions? Okay, well, the last thing we need to do then is add them together, right? My step 3. For step 3, we write down that we're gonna take the complementary function and add it to the particular solution. So again, you can just write this down if you want to. I'll accept that if you just put y sub c of x plus y sub p of x, just in case you want to kind of look at how the final answer would look. It would look like this if you actually put in the expressions. So c1 e to the 2x plus c2 e to the -x, and now we add the particular solution cosine of x minus 3 times sine of x. That's the answer. Step 3 is a nothing step, really. You just have to write down the final answer and you're good to go. Okay. Any questions on that one, guys? All right, well, you know what? We're doing really, really great. I only have a few minutes left. I'm going to try and do one more example. And this example is going to look like the hardest one, but in a minute, I'll explain why it's actually going to be the easiest one. So here's one more example for you, and then we'll call it a day. All right. So the example is solve d squared minus 4d minus 5 of y equals 8x e to the 2x cosine of x minus 3x cubed. Okay, so that's the example. Get all the rest of this out of my way here, so I have room to work. All right, so let's dive right into this one, okay? It looks a little intimidating, but guys, this isn't that bad. This is not actually that bad either. So step 1, we just write down the auxiliary equation. So the auxiliary equation would be r squared minus 4r minus 5 equals 0. Again, we ignore the right-hand side, and we just write down the auxiliary equation by turning the d's into r's. Now, this looks like it might factor nicely, but it actually doesn't. This one does not factor nicely. I'm going to use the quadratic formula to get the roots of this. So let's just see what it would give me. Negative b plus or minus the square root of b squared minus 4ac all over 2a. And so if I put in the numbers that I have, it's going to be 4 plus or minus 16 minus 4ac. Oh, you know what? I'm having a bad problem today with copying my problem incorrectly. Can we go back to the question again, guys? Where I wrote minus 5, I meant to write plus 5. I'm so sorry. I'll blame it on the dark garage I'm working in. That should have been a plus 5. So my auxiliary equation here should have been a plus 5, and I knew that this was supposed to turn out to be 4AC is 20, so I subtract 20 there. So these are the roots. And as you can see, guys, these are imaginary roots. I'm gonna go ahead and clean this up. 4 divided by 2 is 2, and then I have plus or minus. This is the square root of -4, which, as you guys know, that's plus or minus of 2i. Plus and minus of 2i, and when I divide that by 2, it just becomes I. So my roots here are imaginary roots. And so my complementary function is going to be based on these 2 imaginary roots. So let's just remember how we write these solutions down. C1 times, remember that these imaginary roots give us sines and cosines. So I'm going to have e to the 2x cosine of x plus C2 e to the 2x sine of x. This is step 1. Okay. So far, so good? Give me a thumbs up if you are happy so far with what you saw in step 1. Is this all making sense? Let's see. Do we have enough people happy with all this? Some of you are thumbs upping many times. Okay, that must mean you really, really like it. You really get it. Okay, excellent. Yeah, that is it. Guys, step 1 is just going back to the old material. The homework for tomorrow night is basically just step 1. That's all you're doing for Friday's homework assignment, is just doing step 1. Now I want to talk about the annihilator for step 2. The annihilator. Now, and by the way, these are the old roots here. Step 1, those are like what I like to call the old roots. If I look at my table of annihilators for x e to the 2x cosine of x, I'm just going to tell you what it is because I want to make sure I don't run out of time on this. You're going to get d squared minus 4d plus 5, and it's going to be squared because of that x there. And then the annihilator of 3x cubed is actually d to the 4th, right? If I want to annihilate x cubed, I have to take d to the 4th. And remember that we multiply the individual annihilators. And so my new roots that I'm going to get from this annihilator are the following. Notice that this quadratic is actually the same quadratic that we had before. So we're going to get 2 plus or minus I 2 more times. And then we're going to get 0 4 times. These are a whole bunch of new roots that are aligned to this annihilator. And now I'm going to write down the form of the particular solution. Now, here's the thing, guys. If the new roots are repeating the old roots, you have to do that X stacking that I talked about in the last video. So if roots are getting repeated, we have to stack x's here. So my first solution, my first term, I'm going to use an A, and then I see e to the 2x cosine of x, but I have to stack an x in front of that. So it would be x e to the 2x cosine of x. And then plus b times x e to the 2x sine of x. And do you notice that that same pair of roots repeats again for what is actually a third time? So I have to keep going. Cx squared e to the 2x cosine of x and dx squared e to the 2x sine of x. So the point here, guys, is that the x stacking continues based off of the old roots. So if you're repeating roots that were old roots, you still have to stack x's. And then I have 4 more zeros, and I know I'm just about out of time. I'm going to just take 1 more minute. We're almost done. We're almost done. The 4 zeros also require x stacking here. Look at how many constants you have. So E plus fx plus gx squared plus hx cubed, all of this. Does anybody want to take two derivatives of that to be able to plug it into the differential equation and solve for what? A, B, C, D, E, F, G, and H? Technically, that's what you'd have to do. Except, this is my last point for the day, guys. On a lot of problems like this, I'm simply going to ask you to tell me the form of the particular solution. I'm going to allow you to just leave this as your step 2 without taking the time to solve for A, B, C, D, E, F, G, and H, which would be a nightmare. Let me tell you, it would be a terrible nightmare, especially if you didn't have a computer, to solve for these constants. So we're just going to write down the form of the particular solution here and not bother to actually solve for the constants. Read the instructions carefully on next week's homework, because some of those problems, they're just going to tell you to do that. And then finally, the last thing here, guys, and then I'm going to let you go. Step 3 is you just write this down and then you call it good, right? So you just write down y of x equals that, and you don't have to recopy the things in the boxes again. If you just want to write this down, I'll know that you know what you're doing, and I'll be totally okay with that. So I'm trying to make it easy for you. That's it for today, guys. Does anybody have any questions before I sort of sign off from here? I'm going to go over to the Zoom office, though. If anybody wants to talk to me personally, you can come by my office Zoom today, and I'll be glad to talk to you there. But is everybody okay here? Any questions?
I've got a question, Professor.
What's going on?
Yeah, as for the yc of x, why is it multiplied by cosine and sine? Can you explain that, please?
Because of the I here. So if you remember from the video lecture that you watched, if you have the roots a plus or minus bi, you get solutions e to the ax cosine of bx and e to the ax sine of bx. So that's exactly coming from the form of those roots.
Gotcha.
Good enough? Yeah.
Yeah, that's good. Thank you.
Anything else, guys? Hey, thanks for being here. I really appreciate you coming into my garage here in Colorado for a couple of hours today. We will be back in person next week on Tuesday, and I look forward to seeing you there. Let me know if you have any questions on the homework that's due on Friday. I'm definitely happy to help with that as well. But it should go pretty quickly. I imagine you'll get it done in 30 or 45 minutes, something like that. All right, that's it for now, guys. Bye. Have a great rest of your Thursday.
Thank you.
You bet.